Hello students, welcome to the first lecture, online lecture of Statistical Modeling for Business Analytics. I am trying to record the lecture with some, I will have the slides in front of me, and there will also be some amount of board work which I will try to do with a paper. Because I am doing this for the first time, there may be some glitches with the board work or something. I hope you will be able to understand what I am saying in any case. Okay. So what is the topic we will start with today? We are going to talk about panel data. Okay. So this is the outline of the presentation. This is the outline of what we'll talk about. First, we will discuss what panel data is and why it is useful. Then we will talk about panel data with 2 time periods, and then we will talk about something called fixed effects regression, or also entity fixed effects regression. Then we will talk about regression with time fixed effects, and finally we will talk about standard errors, and we will discuss a particular application. And as before, in this course we will explain the whole idea of panel data using this particular application. So before we go any further, first we have to talk about what panel data is. So far when we have been looking, the kind of data we have been looking at is called cross-sectional data. That is, we are looking at several entities or individuals at a given point of time. This kind of data is known as cross-sectional data. Now, you could also look at a single entity over different periods of time. Okay, so you could follow the same entity for different periods of time. So for instance, you could look at how GDP of a particular country is growing over time, or how inflation is growing over time. And this kind of following a particular variable, looking at the values of the variable over time, is called time series data. So on the one hand, you have cross-sectional data, which is for a cross-section of entities at a given point of time. And on the other hand, you have time series data, which is looking at a given entity across different points of time. Now, panel data is combining both. So you are looking at a cross section of entities, and you are following that entire cross section of entities over different points of time. So for instance, suppose the government does a census study. Okay, so it does a census study in 1 year. It goes to many households and asks them questions about different kinds of things, like what their income is, what their consumption is. All of these things it looks in 1 year, say 2001 or something, and then it goes back and asks the same households in another period of time, 2002, and another period of time, 2003. And then when it gathers all of this data together, this data for the same entities followed over a period of time is called panel data. Now, why why is using panel data useful, or why do econometricians follow panel data? That is something we will discuss in a little bit greater detail later on. Okay, so first we talk about we define we give a formal definition for what a panel data set is. A panel data set contains observations on multiple entities. Okay, these entities may be individuals, they may be states, they may be companies, they may be countries. Each of these entities, each entity is observed at 2 or more points in time. Okay, so even if you observe them over just 2 points of time, even that is called panel data. But if you have more number of years that you are observing the same entities, that is, of course, you have a larger panel data set. So what are some of the examples? You remember we talked about the California school districts, the 420 California school districts, where we looked at the class size and the performance of students in those classes. So that at a given point of time, what we looked at originally was the cross-sectional data, where we looked at this data across a cross-section of California school districts at a given point of time. Now, if you went back to those school districts and again measured once in 1999 and again in 2000, so now you have 420 multiplied by 2, that is, you have a total of 840 observations. Okay. Or for instance, you could have data on 50 US states. Each state is observed in 3 years for a total of 150. 50 multiplied by 3, 150 observations. Or you might have data, sometimes you might even have data on individuals. So for instance, if you are looking at, say, individuals who have some kind of a, who are being polled for their opinions, or who have some kind of disease, and you are following them, it's called a cohort study. Okay, so when you have a cohort of individuals, a specific set of individuals, and you keep going back to them and measuring some variables over time, then that would also be known as a panel data. So how do you write, what is the notation for panel data? Okay, so if you remember, when we looked at cross-sectional data, we wrote it as yi is equal to beta 0 plus beta 1 x1 I plus ui. So this is for the ith individual. You have data at a given point of time. Now, since you are measuring the same individual, you are measuring the variables for the same individual over time, you now add another subscript, that is yit is equal to beta 0 plus beta 1 x1 it plus uit. So now you have I and you have t, and you have here also you have I and t, and here also you have I and t. Okay, so the index, the I subscript stands for the ith entity, and the t subscript stands for the tth time. And here we are assuming that there are n number of entities, so I goes from 1 to n, and t, which is a new dimension that we are including, t goes from 1 to capital T. So if you have one regressor, the data is written like this: xit and yit. Okay. So suppose you have k regressors. So you are not only including one variable to explain y, now you are going to multiple regressors. So you have x1 it, x2 it, up to xk it. I goes from 1 to n and t goes from 1 to t. Okay. So it is important to realize that you are observing each entity at different points of time. Okay. Panel data is also known as longitudinal data, and balanced panel indicates that you have data for each of the I entities for each period in time. Okay. So if you were to write it out, in fact we will look at that. So suppose you have okay, this we will talk about when we start discussing the example. Okay. So why are panel data useful? Why do we even look at the same entities at different points of time? So if you remember, one of our concerns when we used cross-sectional data, one of the things that we talked about was that you must try to include all the variables that if you did not include them, then there might be an omitted variable bias. So sometimes though you do not have data for those things, for those omitted variables. Many of you would have done your first project on multiple regression, and many times you said well, this could be the omitted variable bias that we are missing out, and we don't know what to do about it because we don't have data. Okay, so sometimes panel data allows you to control for those variables, even though you do not have data for those directly, and you are not including them in your model, but you might be able to control for them. So what kind of omitted variables might you be able to control for? One kind of omitted variable is something that varies across entities but remains constant over time. Okay, so now let me give you an example. For example, we looked at the school districts, which where you had different kinds of you had different school sizes, class sizes, and you had different class performances. Now, other aspects of the school district, which varies from one school district to another, maybe the number of schools that are there in a particular school district, or the kind of people, the average income of the residents of that school district. Now, these things may differ from one district to another, but may not change over time. If you remember, we said that the income of the parents of the children might have an effect on their performance in the classes. But how do you even, you could try to include the average income, but you are not really interested in the causal effect of income on performance. All you want to do is you want to control for the effect that income might have. So you want to have a control variable. So if in absence of the control variable, you can just say, well, income differs from entity to entity, but over time, the relative levels of income across different school districts may remain the same. So when you want to control for these variables, panel data is useful. These variables may be unobserved or unmeasured. Okay, so the idea is that if the omitted variable does not change over time, then any changes in y over time cannot be caused by the omitted variable. So basically what we are saying is, you take stuff that doesn't change. See, basically you are looking at what effect a change over time of, say, class sizes has over change in performance in class sizes. And there are some other stuff that remains constant over time, and you just control for those variables, and you just look at only things that change over time. There was a bit of a pause over there because the camera stopped working for one of the parts. We are going to start again. We take a particular example of a panel data set, and in this case we are considering the effect of alcohol taxes on traffic deaths. So the idea is basically that if you want to reduce traffic fatalities, one cause of traffic fatalities may be due to drunk driving. If you want to reduce the number of people who are drinking and driving, you may want to increase the prices of alcohol. And so if you impose taxes on alcohol, people may be less, they may buy less alcohol, they may drink less, and they may drink and drive less, as a result of which traffic fatalities may be less. So if the government is sort of trying to look at different policy measures, one of the policy measures they can consider is increasing alcohol taxes. So what do we do in order to see whether there is in fact a causal relationship between alcohol taxes and traffic deaths? What we look at is, we look at data from 48 US states. That is, the number of entities is 48, and we look at two variables from these 48 US states over 7 years. So we have data for 1982, 1988, 1982, 1983, so on and so forth, up to 1988. So this is what the data looks like. So basically we have, say, different columns for the different variables that we might include. Right now we have only two variables that we are looking at. So the first column is for the entity. The second column is for the time period. This column is for the y variable and this column is for the x variable. Entity is denoted by I and time period is denoted by t. Each dependent variable is for the ith entity and the tth time, and the independent variable is also for the ith entity and tth time. So we have, say, suppose the first state we look at is California. We have California data for 1982. Then we have, say, another state which is, say, Arizona. We have data for that in for 1982. Then say we have another state which is Texas and we have data for that also for 1982. Like this we have data for all the states, say Florida 1982. So if you were to look at just 1982 data, this is the familiar cross-sectional data that we know. Okay, but suppose you also have data for each of these states for another year, that is 1983. So this is two time periods. So for each of the states you have data for 1983, you have data for Arizona for 1983, you have data for Texas for 1983, and so on and so forth until you have data for Florida for 1983. Like this you have data for till 1988. So now basically if you when you have just 1 year's data, you call that cross sectional data. When you have many years data, you call that time series data. Okay, so again you have California 1988 and so on and so forth. So what is the total number of data points that you have? You have 7 periods and 48 entities, so you have 336 data points. What is the y variable over here? This is traffic fatality rate. That is the dependent variable that you are interested in, and this is x is alcohol taxes. Alcohol taxes. Both traffic fatality rate and alcohol taxes may vary across entities and also for the same entity over time. So 1982 traffic fatality rate for California may be something, 1983 traffic fatality rate for California may be something else, and 1988 traffic fatality rate for California may be something else. So you may have something like 3% traffic fatality rate, here you may have 2.8%, and here you may have 2.2% and so on. And alcohol taxes may be 1.4%, and here you may have 1.6%, and here you may have 1.8% alcohol taxes. So it is varying over time and it may vary across entities. So Arizona may have, for instance, 2.2% traffic fatality rate, and so on and so forth. Okay, so you may have other independent variables such as x2, this was x1, this is x2 it, this is x3 it, and this would basically be this might be legal driving age. Of course, the point is that legal driving age may not be something that changes over time. Legal driving age, drunk driving laws, this may change or not change. What might be some of the drunk driving laws? So for instance, in some states, if you drink and drive, your driver's license may be suspended. Some other states, if you drink and drive and cause an accident and as a result someone dies, you may be sent to jail because of manslaughter, So the severity of the punishment that you might get if you drink and drive, these laws may change from state to state. So these might be the other variables that you are looking at. Now, if you were to just take the traffic fatality rate and the alcohol taxes and take all of the data together without sort of giving taking into account the fact that you have the same entity measured over different years, you don't take into account that particular specific detail, but you just take them all as if it is a cross sectional data, and you plot fatality rate on the y axis and beer tax on the x axis. So as you can see, the beer tax goes from around $0 per case to around $3 per case, and fatality rate goes from around 0 fatalities per 10,000 to around 4.5 fatalities or 4.25 fatalities per 10,000. Okay, but if you were to just plot the data like this, as if it were, this is called pooled data. Okay, so if you were to plot the data like this, you find that the fatality rate is related to the beer tax, but the coefficient is positive. So basically what you are finding is that the coefficient is 0.15. So what is going on here? As the alcohol taxes goes up, there are more traffic deaths. Does this sound reasonable to you? Possibly not, right? So we will look at it a little bit more. So why might there be higher or more traffic deaths in states that have higher alcohol taxes? So there may be other factors that determine traffic fatality rate. So one may be the quality of automobiles that people are driving in that particular state. So some state that has higher income per capita, those individuals may be able to afford higher, better quality automobile. So both the person who is driving the car that caused the accident and the car in which the person who had an accident or who was hit by another car, both those cars, if they are of higher quality, then possibly no one may die. The airbag may deploy, or the body of the car may be stronger or something. It may not be a very old car, the car that is driving, the driver's car, that may not skid or something like that. So as the quality of automobiles increases, which is possibly dependent on the per capita GDP of that particular state, as the quality increases, the number of fatalities may go down. Quality of roads. Now, obviously, as the quality of roads increases and the roads are maintained better and the visibility is higher, there are better markings on the road. So then also you expect that these will help drivers be more careful. It will help drivers be able to drive better. They will not lose control of their car, and they will be able to see oncoming traffic, as a result of which so many accidents may not be caused, and because of this the fatalities may be less. But see, this has nothing to do with drunk driving. This is uh, an independent variable, which is probably a function of which is probably a characteristic of the state that we are talking about. Another thing might be the culture around drinking and driving. So a particular state may have a bit of a lax culture where people party a lot. Drinking and driving is not considered to be a very bad thing socially. People tend to do that. So you may have some states, I mean, if I say such things, I don't know whether it is completely true or not, but some of the states like Florida, where young people may go to party, over there it may be that there is a culture around drinking and driving, which may lead to greater fatalities. I am not particularly fully sure of this, but I'm just throwing it out as a possible idea. Another thing, of course, that will affect fatalities would be the density of cars on the road. As the density of cars increases, the probability of accidents increases, and the probability of fatal accidents also would increase. Okay, so all of these are extraneous factors that might affect the fatality rates. Remember that when we are looking at fatality rates, the we only have access to data about fatality rates. We do not have access to data about the cause of the accident, which caused that particular accident, which led to the fatality. So if we had directly, drunk driving caused accidents, then that would make our job a lot simpler. But what we do not have access to such data at such great detail. We do have access to data at a more aggregated level, which is basically the traffic fatality rates. So, these omitted factors that we just talked about, that was the traffic density, the culture around drinking and driving, quality of automobiles, quality of the road, these factors could cause omitted variable bias. So, let us take one particular example. Now, if you remember from our early lectures, what are the conditions for an omitted variable bias to happen? Um, for the omitted variable, suppose your variable of interest is x1. Okay, so suppose your variable of interest is x1, plus yi equals to beta 0 plus beta 1 xi plus ui. Okay, you have included x1 and you are trying to see the effect of x1 on y, x1 on y. You have omitted some variables which are x2, x3, and so on and so forth, x4. For x2 to be an omitted variable, x2 should be a causal factor for xy, causal factor for y. It should have causation for y, and x2 should be correlated with x1, right? So these are the two conditions for x1 and x2, for x2 to be an omitted variable. Now let us look at high traffic density. High traffic density means more traffic deaths. So this is your y variable, traffic deaths. So high traffic density has a causal factor for it, is a causal relationship towards y. Also, certain states that have lower traffic density tend to have lower alcohol taxes. So, in this particular case, the western states which have lower traffic density also have lower alcohol taxes. So, x2 happens to be correlated with x1 also. Even though there isn't a particular causal relationship that we are finding over there. The two conditions for omitted variable bias are satisfied. Specifically, high taxes could reflect high traffic density, so the OLS coefficient would be biased positively. That is, high taxes, more deaths. If we leave out high traffic density as one of the omitted variables. So, what should we have done if we were not looking at panel data? We would have included this variable. So, we would have said beta 0 plus beta 1 x1i plus beta 2 x2i plus ui, where x2 is now traffic density. Okay. And x1 is beer taxes. And yi is fatality. So like this, we could include all of these other variables that we talked about. But it's suppose you don't have data for traffic density, or you don't have data for culture, or you don't have data for the quality of roads. So what you do is you introduce the idea that you could use a proxy variable, that is z, which is a proxy variable, which is an indicator variable for each entity. Proxy variable, indicator for each entity I. Okay, so now each entity I, each state in the United States differs from each other in certain ways, and these differences don't change over time. So traffic density in certain states may be always high compared to certain other states. There may be small changes, but overall the traffic density, the average traffic density in a particular state may not change much over time. Similarly, the culture about drinking and driving may not change over time. So you take all these factors and you say each state has a certain characteristic which leads to people there being a greater chance of people drinking and driving, or there may be a greater chance of fatalities which are specific to that particular state. So you include that as a proxy variable. So panel data lets us eliminate, when you include such a thing as a proxy variable, all of these variables are included, and it allows you to avoid omitted variable bias. Similarly, the second example is of cultural attitudes towards drinking and driving. Again, cultural attitudes are a determinant of traffic deaths. So X3 is a determinant of Y, and X3 is probably associated with X1, that is where people are more lax about drinking and driving. In those states, maybe the beer tax is also lower. So the two conditions are satisfied. So high taxes could pick up the effect of cultural attitudes towards drinking. So if you don't include this variable, you will have the beta 1 for the taxes will be biased. Okay, again, panel data, as we said, if you include a proxy variable, then it will include the effect of the cultural attitudes, and it will let you avoid omitted variable bias. So first we start with a simple 2 time period panel data. We do not look at, here we had said, here we had looked at 82, 83 and so on till 88. But first, in order to understand it at a simple level, we start with 2 time periods. So fatality rate IT is equal to beta 0 plus beta 1 beer tax IT plus beta 2 ZI. Now look at this, plus UIT. You will notice that fatality rate has a subscript I and T for the ith entity at the tth time. Beer tax has a subscript of I and T for the ith entity and the tth time. It is changing across entities and it is changing across time. But ZI, while it is changing, it has only a subscript of I. It is changing across entities, but it is not changing across time. It is staying constant over time. That this is what is being said here. ZI is a factor that does not change over time, say traffic density or culture, at least during the years on which we have data. Suppose ZI is not observed, so its omission could result in omitted variable bias. The effect of ZI can be eliminated using t equals to 2 years. Let us see how that can be done. So basically, when we have only 2 years, we are, instead of modeling the absolute values of traffic fatality rate and beer tax, we will model the change in traffic fatality rate from 1 year to the next and the change in beer tax from 1 year to the next. So this is what we are doing. Any change in the fatality rate from 1982 to 1988 cannot be caused by ZI, because ZI by assumption does not change between 1982 and 1988. So basically what we are saying is any change in beer tax over time will, of the ith entity on the fatality rate, or change in fatality rate of the ith entity over time, cannot be caused by ZI, because ZI does not change over time. So we have fatality rate I 1988 specified as beta 0 plus beta 1 beer tax I 1988 plus beta 2 ZI plus UI 1988. Again, fatality rate I 1982 is beta 0 plus beta 1 beer tax I 1982 plus beta 2 ZI plus UI 1982. So suppose after taking into account beer tax and ZI, whatever error you have, that is completely random. Okay, it has random and it has zero mean. As if you remember, one of the necessities for one of the assumptions for performing OLS is that your conditional mean, given that you have included whatever conditional mean of the error term after including all the other terms, the conditional mean of the error term should be 0. So this is what we are saying. Expected value of UIT given beer tax IT and ZI is equal to 0. So if you subtract this equation 1982 from this equation 1988, that is 1988 minus 1982, it eliminates the effect of Zi because these two terms cancel out and beta 0 also cancels out. So what do we find? We find fatality rate I 1988 minus fatality rate I 1982 is beta 1 beer tax I 1988 minus beer tax I 1982. Notice that beta zeros have cancelled out and beta 2 Zi's have cancelled out, and error term UI 1988 minus UI 1982, this is what you have it left over here. Now see, UI 1988 conditional mean given these two is 0. The conditional mean of UI 1982 given these two is 0. So this minus this, the conditional mean of that will also be 0 given beer tax 1988 minus any arithmetic operation on that will also lead to the conditional mean being 0. Okay. So this difference equation, now we have a difference equation, fatality rate minus fatality rate 1982, 1 year minus the other year is equal to beta 1 beer tax 1988 minus 1982. The omitted variable Zi doesn't change, so it cannot be determinant of the change in Y. So what do you do now? This difference regression doesn't have an intercept. It is eliminated by the subtraction step. So basically what you are doing is, if you were to look at over here, what you do is you include another variable. So you include, when you are looking at only 2 time periods, you include a change variable. So you do del y it del x1 it, okay, and basically you say del y I 1983 minus 1982 and 1983 minus 1982. So you have 2.8% minus 3%, that is minus 0.2%, and 1.6% minus 1.4%, you have plus 0.2%. Similarly, if you had over here 2.4% and you had over here you had 2% and you had 1.7%. So you would have 2.2 to 2.4, you have 0.2% and you have minus 0.3%. So now you are creating another changes dependent variable. This is your new dependent variable. This is your new independent variable, and you can regress del y over del x1 and you can get your new equation. So let us look how this happens. So if you were to not do the changes data and you just use 1982 data, cross-sectional data, and you regressed fatality rate over beer tax, you would have 2.01. The estimated equation is written like this. Fatality rate that is estimated is 2.01 plus 0.15 into beer tax. Okay. So the standard error for beta 0 is 0.15. The standard error for beta 1 is 0.13. And you will notice that this is not statistically significant because 0.15 by 0.13 is not 1.96. But it had to be statistically significant at a 95% confidence interval. It needs to be equal to or greater than 1.96. Now, similarly for 1988 data, if you were to just estimate it as a cross-sectional data, you would get this estimated equation. When you do the difference regression, FR 1988 minus FR 1982 regressed over tax 1988, beer tax 1988 minus beer tax 1982, you get this new equation. Now notice that the beta coefficient, it was positive over here and it has become negative over here. Over here the brackets have shifted a bit. This is actually the standard error for this, and this is the standard error for this. Okay, and you will notice that over here it is definitely statistically significant. So if you put changes in fatality rate on your y-axis and changes in beer tax on your x-axis, and you plot the data along with the regressed line, you find that the regressed line is now has a negative slope. Okay. Now we will come to, but this is this kind of two periods data. We just talked about two time periods. What happens if you have more than two time periods? In that case, you cannot do the changes specification, because changes was only from one period to the next. What do you do when you have that one to the next? Which change do you look at? Or do you do it from 1 year to the next? It doesn't seem like you will get several beta coefficients. That doesn't seem like an efficient way of doing it. So what do you do if you have more than two time periods? You specify a regression model where you say yit is equal to beta 0 plus beta 1 xit plus beta 2 zi. You remember the proxy variable that I was talking about? This is the beta 2 zi. So plus uit. So there will be you can so you can, it is a proxy variable. It could either, you could just do it using n minus 1 binary regressors. What is a binary regressor? It's a dummy variable. So you remember, if you have 48 states, you could include 47 dummy variables, one for each entity. That is the n minus 1 binary regressor model. Or you could do it using something called the fixed effects regression model. So first we will talk about the fixed effects form. So the model is specified as follows. Yit is beta 0 plus, this is the population regression function, beta 0 plus beta 1 xit plus beta 2 zi plus uit. So this is, now suppose we say we are only looking at California. Population regression for California. We are taking only, we substitute California for I everywhere. So ycat is equal to beta 0 plus beta 1 xcat plus beta 2 zca plus ucat. So in some sense, this is like a time series data for California. So California, you have data for 1982, 83, 84, 85. So it is like one entity you are following through time. Okay. Over here, what happens is, see, this is not a function of t. So it doesn't change over t. Here, the y variable is only changing over t. So beta 0 plus beta 2 zca, you take within the bracket. That is a new intercept, which is dependent upon the constant intercept beta 0, and then some part of that intercept is dependent upon the fact that this particular equation is only for the California state. So you have beta 0 plus beta 2 zca. This is your new intercept. This intercept is specific to California, plus beta 1 xcat plus ucat. So you have ycat is alpha cat. We are introducing a new parameter alpha compared to beta, just to differentiate it from beta. Beta is common across all entities, but this is specific for California. So alpha Ca plus beta 1 xcat plus ucat. Alpha Ca, beta 0 plus beta 2 zca doesn't change over time. And now this zca can include within it all the aspects about California which do not change over time. For instance, the weather of California, the fact that California is on the western side of the US, the fact that, California, the GSDP is higher compared to some other states. Okay, it is on the western coast. All of these things, the quality of roads comparative to other states may not change, the relative quality of roads may not change so much. So all the factors about ZCA that does not change over time is captured within this new intercept. So alpha Ca is the intercept for Ca, and beta 1 is the slope. Beta 1, you will notice, is dependent both on the fact that it is for Ca and on the and on the time intercept. The intercept is unique to CA, but the slope is the same in all the states, parallel lines. Okay, we will see how that works. If instead of California you take Texas, so you have the same equation as above, except wherever it was for California, you substitute with Texas. So you have ytxt comma t is equal to beta 0 plus beta 1 x Texas comma t plus beta 2 z Texas plus u Texas comma t. Now again you take the constant terms beta 0 plus beta 2 z tx, you take them out, and you have plus beta 1 x Texas comma t plus u Texas comma t. So y Texas comma t is a new coefficient which is specific to Texas. Hence it is denoted by alpha subscript Texas plus beta 1 x Texas comma t plus u Texas comma t. Now you do a similar thing from Massachusetts. Here we had started, I forgot to say right at the beginning that we are considering only 3 states in the beginning, okay, to simplify the discussion. So y California comma t is equal to alpha California plus beta 1 x California comma t plus u California comma t. Similarly for Texas you have alpha Texas. For Massachusetts you have alpha Massachusetts. So you can, or in order to be more general, you can call it as yit is alpha I, which is dependent upon the ith entity, plus beta 1 xit. It depends. Now just see that beta 1, the coefficient for beta 1 across the all the states remains the same. So as we said before, there may be a slight break because I'm recording part of the lecture again. So for generality, we say yit is equal to alpha I plus beta 1 xit plus uit. Let us look at how this would look if we plotted, looked at the 3 regression lines. So the regression lines for each state in the picture, if you plot it, it will look like 3 parallel lines, and they have different intercepts. As you can see, the intercept for alpha California is here, intercept for alpha Texas is over here, and intercept for alpha Massachusetts is over here. Okay, so the slopes remain the same. The slopes for each of these lines remains as beta 1x, here also beta 1x, here also beta 1x. So as you this may remind you of other cases where we have used dummy variables. For instance, one of the cases where we used a dummy variable for gender, when we were looking at the effect of education, number of years of education on the income that an individual earns, and we added a dummy variable for whether that individual was a man or a woman. Then we found that if you just included the dummy variable for the gender, you might get 2 parallel lines, one for men and one for women. Okay, so these shifts in the intercept can be also represented. Either you can use it in this format where you specify a different intercept for each regression line, or you can also do it using binary regressors. Okay, so this is how. So now in the binary regressor form, you could specify a common intercept, and you could include dummy variables for California and for Texas. In this particular case, you are considering 3 states: California, Texas, and Massachusetts. Since you are considering 3 states, you drop one of the states, that is, you drop Massachusetts, and you include a dummy variable for California and a dummy variable for Texas, and then your independent variable of interest and your error term. So the dummy variable for California will take a value of 1 if the state is California and 0 otherwise, and dummy variable for Texas will take a value of 1 if the state is Texas and 0 otherwise. And you leave out the Massachusetts, because otherwise you will run into a dummy variable trap, because there will be perfect multicollinearity. This is something that you are familiar from our discussions beforehand. So to summarize, there are two ways to write the fixed effects model. One is the n-1 binary regressor form, where yit is equal to beta 0 plus beta 1 xit plus gamma 2 d2i up to gamma n dni. You will notice that we have dropped the d1 category and all the other categories are included. In the fixed effect form, you write yit as equal to beta 1 xit plus alpha I plus uit, where alpha I is called the state fixed effect or state effect. That is, it is the effect of it is how much the average fatality rate is higher because of the fact that the data is recorded from a particular state. Now, how do you estimate this? So there are again three estimation methods. You could include the n-1 binary regressors. You could do it using OLS regression. There is something called the entity demeaned OLS regression, and we will discuss what that is. Or you could do the changes specification if you have only two time periods. Okay, so in the changes specification, as we discussed before, you do not need an intercept. So you regress the changes in fatality rate over the changes in beer taxes. These three methods produce identical estimates of the regression coefficients and identical standard errors. So we did the changes specification already, and methods 1 and 2 work for general time period, not just for t equals to 2. Okay, and method 1 is only practical. You can use n-1 binary regressors when n isn't too big. So for instance, in this particular case, you have 48 US states. So you include 47 dummy variables, n-1. Okay. But suppose you are looking at, have panel data for 1,000 households which have been followed over a period of time. Now, in order to include a dummy variable for each entity, you would have to include 999 dummy variables. So you can imagine that would be a very awkward looking equation, and it would be sort of silly to do that. So in that particular case, what you do is you do something called the entity demeaned OLS regression, and we will discuss how that goes. So the n-1 binary regressors OLS regression, you specify your model like this: yit is beta 0 plus beta 1 xit plus gamma 2 d2i up to gamma n dni plus uit. First we create, how do you do it? You create the dummy variables. Then you estimate this equation by including all of those dummy variables. And then you perform your hypothesis test and you look at your confidence intervals in the same way as with normal OLS regression, with multiple regression, and you use heteroscedasticity robust standard errors. In case there is heteroscedasticity, you just use heteroscedasticity standard errors. So this kind of method is impractical when you have a very large number of entities that you are looking at. Now we look at something that is called entity demeaned OLS regression. Now, in the fixed effects regression model, we said yit is equal to beta 1 xit plus some entity level effect, which is denoted by alpha I plus uit. Now, basically what we are trying to do, when you sum up this entire all the data points over time and divide by t, that is, you look at the average fatality rate, how it is related to the average beer tax over time, then that will also satisfy, because all you are doing is an arithmetic you are doing some arithmetic calculations over there, here computations. Okay, so it will not change anything if you summarize it over time and you uh, divide the whole thing by time t, then this is what your equation will look like. Now what so basically what you do is you are interested in the average over time values for xit and yit for a given entity I. Okay. So average yit x. So you create something called xt bar, not for, is equal to, for the ith entity is summation t equals to 1 to t capital T divided by 1 by t xit, and y t bar for the ith entity is 1 by t capital T equals to 1 to t y I t. Okay. So you are basically saying, suppose you say you take a particular entity, California. Now California, you have uh, 1982 data, 1983 data, so on and so forth, up to 1988 data. YIT is, say, fatality rate is 2.2%, you have 2.19%, you have 3%, whatever. The California fatality rates are like this. You take the average of all of this. So you sum it up over time and you divide. So you have 1 by 7 multiplied by 2.2% plus so on and so forth up to 3.0%. Similarly, you do XIT, you sum it up and you divide it by the total. So XIT says 1.4%, 1.8%. You sum it up and you have the average over time. Now, basically what you are trying to do is, you are trying to subtract the averaged quantity, the averaged fatality rate and the averaged beer tax from the from each of these data points. So suppose your average fatality rate comes out to be 2% and your average beer tax comes out to be 1.5%. So from each case you do 2.2% minus 2%, that is 0.2%. So this is called the entity demeaned, that is you are subtracting the average. You are taking away the mean. So entity demeaned value, and 2.19%, this is 0.19%, this is 1%. This is the entity demeaned y variable and this is the entity demeaned x variable. This is minus 0.1%, this is 0.3% and so on. Okay. So these are the entity demeaned values. So deviation. So here we are talking about deviation from entity averages. You are taking the average and you are taking away the average from the. So basically the idea is this. You are not really interested in the absolute values, but the variation in the specific year quantities from the average of that particular entity. So this is what you do. You demean this thing, and if you do that, now what will happen? Basically, you are subtracting this minus this. Alpha I and alpha I are being cancelled. UIT minus 1 by T UIT. So this is what you have. Beta 1 into XIT minus 1 by T X summation XIT. So this is what you have. So you call this new new variable you call it y tilde it, and this new variable you call it x tilde it, and y tilde it is equal to beta 1 x tilde it plus u tilde it. So these are just new variables that you have created. Just like you did it in the changes specification, you created a new dependent variable and a new independent variable. Here also you are creating new dependent variables. These x tilde it and y tilde it are called entity demeaned data. Okay, you are taking away the mean for that particular entity. So for I equals to 1 and t equals to 1982, y tilde it is the difference between the fatality rate in Alabama in 1982 and its average value in Alabama averaged over all 7 years. So this is what y tilde it is this. First we construct the entity. How do you estimate it? You construct the entity demeaned variables yit tilde and xit tilde. Then estimate 2 by regressing yit tilde on xit tilde using OLS. Like the changes approach as I said before. And standard errors need to be computed in a way that accounts for the panel nature of the data set. Okay. So this can be done in a single command in Stata, or it can be done in R also, okay, by creating a panel data object. The reason this works is basically we are trying to say is that if beer taxes were increased in a particular year, in a particular state, keeping all the other factors about that state constant, such as the quality of roads, the culture of drinking and driving, did the fatality rate actually change? Because 1 year compared to the averages in other years, in 1 year the beer taxes were increased. So did the fatality rate either go down or go up, or how did it work? Okay, so this is how it works. Traffic deaths and beer taxes in Stata, you let Stata know you're working with panel data. Okay, and you create a panel object. This you do in R also, and you indicate which is your entity, what is your entity and which is your time variable. Then you regress fatality rate over beer taxes, and in this particular case you get a coefficient, as you can see, minus 0.6558736. So what we expected, that as beer taxes went up, your fatality rate would go down. So that is what we are seeing, and it is also statistically significant. As we can see, it is statistically significant at the 95% confidence level. So, so this is what for n equals to 48, t equals to 7. This is how it is, minus 0.66 beer tax plus state fixed effects. There are some state fixed effects. This is, we are not really worried about it, but there are some state fixed effects. So should you, how many binary regressors would you include to estimate this using the binary regressor method? As we said, you would include 48 minus 1, 47 binary regressors. So if we compare this with the 2 years data, that 2 years changes specification, if we had only time t equals to 2, we can see that actually the coefficient was much higher in that particular case. The coefficient in terms of magnitude, the coefficient was larger over there, while the coefficient here is 0.66. Now here is some data about the different beer taxes in different states of the US. This is for your interest if you want to look at it. Okay, so we will stop here for now, and the next will be in the next lecture.